This lecture gives a short discussion about the relation between direct sums and quotient spaces. So let's start with a discussion of the internal direct sum of two subspaces of a vector space. So let's say we have given two subspaces, U and W, of a vector space V. What does it mean that the vector space V is equal to the direct sum of its two subspaces? So this is actually the internal viewpoint in this case. Well, that means that on one hand the vector space V is the sum, where the sum is just defined as the vector space of all U plus W, where U is in U and W is in W. Or in other words, that means that every vector V in my vector space can be written as the sum of a vector in U and a vector in W. And the second condition, which makes the sum direct, is that if we look at the intersection of the two subspaces, that will be the zero space alone. This precisely means that this presentation of the vector V as a sum is unique. Namely, if I can write a vector in the form U1 plus W1 and also in the form U2 plus W2, where the two U's are in U and the two W's are in W, then of course can write U1 minus U2 is equal to W2 minus W1. And now you see U and W are both subspaces. So that means that the difference of two vectors from U is in U, the difference from two vectors in W is in W. So that means that this vector is in U intersected with W, which we assume to be the zero space, and that means it follows that U1 is equal to U2 and W1 is equal to W2, or in other words, that the presentation of V, a vector, now an arbitrary vector in my vector space, as the sum of two vectors, one from U and one from W, is unique. So let's also review the definition of a quotient space. So here we have a subspace U of a vector space V. So this is now a single subspace of a vector space V. And then what we do is we consider sets of the following form. We take the subspace and we add vectors from the vector space V to that subspace. So what that means is we look at certain sets. So this is the set of all U plus V, where U runs through the whole subspace U. So this will be a subset of the vector space V. So have in mind the standard picture where we have V is the whole plane R2, and where we have a subspace U that represented by a line through the origin. Then taking such a set means we pick a vector V and we add to that vector V arbitrary vectors from the subspace U, and of course you get a line which is parallel to the line U through the origin. So this will be precisely U plus V. And the next step is the most important one. We now define a set V by U to be the collection of all these subsets of the vector space V. So this will be the set of all U plus V, where now V is an element in my vector space V. So the elements of this set now are called cosets. So here we have drawn one example of a coset of the subspace U. And it turns out that this collection of subsets of V now carries the structure of a vector space. So we can make this set to become a vector space, using addition and multiplication by scalars in the vector space V. So if you take a u plus v1 and a u plus v2, and when I write that up, you have to have in mind that each time this is just one element now in v by u. So this is a vector in v by u. This is the second vector in v by u. And now I define their sum to be, I take the sum of the two vectors in my vector space, and then I add that to u. And this becomes a new coset. And I define the multiplication of a scalar by such a coset by multiplying the vector v by the scalar r and taking the corresponding coset. And now you can sit down and can prove that this makes sense. There's some work to be involved. For example, and that is the most important thing, the representation of cosets in the form u plus v is not unique. The element that I'm looking at, the vector in my vector space, is this set. And it might be represented in the form u plus v1 or in the form u plus v1 prime, let's say. And it will be if and only if v1 prime minus v1 is in the set u. Because what we have here is set equality. And like a very easy example, I mean that one has to kind of like get used to this kind of thing is, if I take the vector v itself in u, then of course u plus v, this set will be equal to the set u. And this is actually then in this case, u plus v is the zero vector in our vector space. Because adding the set u to a set u plus v, this is just the set u plus v. This follows from the vector space property because sums of vectors in a subspace are again contained in the subspace. And like here, this set equality, just think about that. The vector v plus any vector in the subspace u, if the vector v is itself in the subspace, will be a vector in the subspace u. So if you do not believe these set equalities, you always have to check them by checking both inclusions, right? So you have to think about, why does u plus v subset u hold? Well, as I said, v is in u, so if I add any vector in u to the vector v, I will get a vector in u. So this is this set equality. But of course, you can write every vector in u, if you pick one, right? I can write that vector in the form u minus v, which will be a vector in u plus v, and that will be a vector in u plus v. So that is precisely the other inclusion. So let's start with an example we're maybe a little bit more familiar with. So let's say we start with a vector space v is equal to R2. So all pairs of real numbers, and we think of this as the real plane. And let's say we have given the subspace U to be the set of all pairs x, 0, where x is a real number, runs through all the real numbers. So this is now a subspace, of course, of V. That is just the real line. And then there are all what we call complementary subspaces. So what are complementary, what are complements to the subspace U? Well, these are arbitrary subspaces through the origin. So let's see, this is my subspace U, then that subspace V will satisfy the condition that, well, that's actually a subcomplement W, that's what I want, complement W. The whole space was the vector space V. So then what we get is that U plus W is equal to V, and that's an internal direct sum. So in this case we call the two subspaces complementary. But the point is, if we start with a subspace U, there's no canonical choice for a subspace W. There are many. Any line through the origin will satisfy the very same purpose. Just think about it. Now, the point is to find a vector space which will not be a subspace of the vector space V, but which is in a certain way naturally isomorphic to all possible complements of the subspace U. And here's the idea. Just look at all lines parallel to the subspace U. Notice that if we have such a complement W, then each of these lines will intersect the subspace W in a unique point. So the lines which are parallel to U will be in one-to-one correspondence to the points of this complementary subspace W. This is precisely the idea. So what we do is we introduce V by W, or actually V by U. So we introduce the subspace V by U, and that subspace will consist of all these parallel lines which are parallel to U, which I said we can write in this form, U plus V, where V runs through all of V. And then this subspace turns out is isomorphic to W for each complementary subspace. And here's the proof for that, which is in fact not very hard. So here's a more precise statement of that theorem. So let's say we have U and W, and those are two complementary subspaces. It comes from complement. Complementary subspaces of a vector space V. So again, remember that just means U direct sum plus W is equal to V. Then the map, and now we just write up the map that I kind of like have been talking about a second ago, which takes a vector W in the subspace W and maps that vector to the vector W plus U. So have that picture in mind right here. This was our picture for U. Here we had our picture for W. Now what I do is I take any vector in W and I add to that vector the subspace U, and this assignment is precisely this, which takes the vector W and maps that vector W in our complementary subspace to W plus U. Well, actually our book prefers what is called the other type of coset, so U plus W, and that is then an element in V by U, and the claim is that this is an isomorphism. So there's a whole thing, there's a couple of things to think about. Mostly it's that the mapping is linear. It's kind of, the map is linear, follows essentially from the way we have defined the vector space structure on V by U. Let me not talk about that, but let me briefly look at why this map is one-to-one or injective and why it's onto. Well, if you take W1 and W2, so if we have two different vectors in our subspace W here, so you pick a W1 and a W2 in there, and then let's assume U plus W1 equals U plus W2. So the image under our suggested map here, right? I mean, of course, if you want, you can give it a name. If you call that map eta, right, then this is The first thing is eta of W1 here. So we assume eta of W1 is equal to eta of W2, and we want to prove W1 is equal to W2. Now what that means is that, this set equality, of course, tells us that if we look at the difference vector, W2 minus W1, that will be a vector in U. But the difference vector was also, both vectors were in W, so the difference vector is also in W. So that's a vector in the intersection. And the fact that these two subspaces are complementary meant precisely that that intersection only consisted of the zero vector. So this means, of course, that W1 is equal to W2. And that proves precisely that our map eta is 1-to-1. So the next thing is would be to think about why this map is in fact onto, which is also quite easy. If you take any vector v in v, then because we know u and w are complementary subspaces, I know I can write that vector v in v in the form u plus w, where u is in u and w is in w. So what does that mean? That means that if all the elements in v by u in that quotient space have the form u plus w, right? But u plus v will run through all possible cosets in v by u, and this can be written in the form u plus w. But since u is a subspace, the big U is a subspace, this is of course the same thing as u plus w, and this is eta of w. And this precisely shows that our map eta is onto. And this proves that this natural map, from the subspace to the quotient space, is an isomorphism. So the quotient space is not as natural because it's not a subspace of V, but it practically is in a very natural way isomorphic to every complementary subspace to the subspace U. So here's an easy consequence of this. If you have a subspace U of a vector space V, then the dimension of the quotient space V by U is equal to the dimension of V minus the dimension of U. Well, how can you do that? Well, we know if we have a subspace U of a vector space V, we can always find a complementary subspace. How does that work? Well, remember, we can take a basis, let's call that basis u1 up to un of the subspace U by vectors, so this is supposed to be a basis of U, by vectors, let's see, u1 up to un, w1 up to wm, to a basis of the whole space, basis of V. And now I can define the subspace W to be the span of the vectors w1 up to wm. Then that will be another subspace of V. And in fact, U plus W, the direct sum of these spaces, will be equal to the subspace V. That's an internal direct sum. Surely every vector in V now, because the collection of all vectors here is a basis, so every vector in V is a sum of these basis vectors. And if you would have something in the intersection of U and W, it would be both a linear combination of U vectors and the combination of W vectors. But because this is a basis, all the coefficients would have to be zero if that would be the case, right? Because you can represent the zero vector never as a non-trivial linear combination of all the vectors. But you see, now we're almost done, because we know that the dimension of V is equal to the dimension of U plus the dimension of W. We actually have to just look at how we actually constructed the vector space W for this to be the case. But we know that our subspace W is isomorphic to the vector space V by U, whatever W, whatever choice of basis vectors we have taken there. So you see this is equal to the dimension of U plus the dimension of V by U. And this proves our formula. Just kind of subtract the dimension of U on both sides of this formula.